screen?
Yes, yeah, we can see your screen fine. Thank you.
Okay, so in the EE exercise, we requested for 4 states, 4 singlets and 4 triplets in all the 4 symmetry blocks. So in your output file, you will see this type of sections for each of the excited states. So here, this is the excited state in the A1 block, and you can fetch the excitation energy from here. And these are the amplitudes which are involved in the transition. So these are the orbitals involved in the transition. And in the transition properties section, you can get the oscillator strength, which determines how bright a transition is. So for all our 8 excited states, 4 singlets and 4 triplets, we are listing the excitation energy and the oscillator strengths here. So this is the brightest transition among the singlets. And for the triplet transition states, you can see that the oscillator strength is 0 because they are spin forbidden. So one important thing is that you can even compute the transition between the excited states. Then for your for your future purpose, here we are listing some of the natural transition orbitals, which are very much important to visualize the transitions. But these are for your future purpose. You can't currently do it with the help of IQmol. So yeah, that's it.
Can you see my screen? Yeah, so I'm analyzing the CVS, EOM, IP, and E outputs here. So the first one is how you analyze the CVS IP. Here you can get the excitation energy at the carbon edge and also the orbital involved in this transition. So here from the Dyson orbital, we can see that it is a carbon S orbital where the core ionization is happening. Similarly, in CVS EOM-EE, you can get the excitation energy and also the configurations or the orbitals involved in this excitation. And as we had told in CVS EOM-EE, we can also request for the transition properties. Here, what we are looking for is the oscillator strength, which shows how bright the transition is. And also you can get the dipole moment as well. And the same analysis can be done for CVS, EOM, IP, and EE at oxygen edge as well. One important thing to notice here is, as Professor Krylov had mentioned about core orbitals, that they are very compact and specialized that can be understood from analyzing the energies. So this is basically the analysis of CVS, EOM, IP, and EE calculation.
All right, welcome back, everyone. So if you set up the calculation correctly, you should get something like this for your output. So you should get the list of transitions with their symmetry. What you need to be careful about this section is that in Q-Chem you get printed the symmetry of the transition, but within EOM-SF and starting from a triplet state, this will not be the symmetry of your target state. So if you make use of the product table of the symmetries, you can easily get what is going to be the symmetry of your target state. So this is I'm putting everything here in this table. So basically, when you get an A1 EREP for your transition, this means that your state is actually going to be of B2 symmetry. In here, you can also see the character of the transition with the orbital representation. And the other thing that you need to be careful is the spin multiplicity of your state. Again, you need to be sure that your EOM states are either singlet triplets and for sure that they're not spin contaminated. So if you do this for all the transitions that you calculated, you can organize them. So these are the transition printed in the output. These are the real symmetries of your target states. These are the excitation energies that are printed in the output, but these are not going to be the excitation energies that you need to actually care of, because these are the energy difference between the coupled cluster wave functions and the EOM states. But for this tutorial, we want the energy difference between EOM states, specifically from the triplet state to singlet states. So all I did here was setting this state, since it is the only triplet state that I have, to 0. So I shifted all these energies by 0.0086 eV. And these are then the excitation energies with respect to the lowest triplet state, which means that these are the singlet triplet gaps. And that was the tutorial.
Okay, so I have here the summary about the so I have the summary of the EOM electron attachment for the magnesium hydroxide example. In this case, you look in the output for the line beginning with EOM EA transition, which starts the listing of the target states. What it shows is that what you can see, it shows the excitation energy. And this is just as in the spin flip case that Gohan has just described, a value that's irrelevant in here, as it shows the excitation energy from the cationic reference to the EOM target states. In this neutral molecule, I mentioned that both ground and excited states are described by the EOM states. Therefore, in order to get the spectroscopically available transition that will make appearance in, for example, absorption spectrum, you have to subtract those energies to get the spectroscopic excitation energies. Another thing in this example was the Dyson orbitals. To see them, you have to open the output, and in the IQ-mol on the left panel, you can go to surfaces and then see where the densities associated with this unpaired electron are localized in the molecule. In the case of EM double electron attachment, what I would like to bring your attention to is that there will be separate listing for singlet and triplet states. So you would like to look for lines which say solving EM-DEA CCSD for selected transition for singlet, and then separately they will be listing for triplets. And that's where you can get this multiplicity sign in here. The other element that was part of this example are the transition properties, this time between the various EM target states. And here is an example listing. Those transition properties can be found by looking for the state A double dot, which shows the transition, which shows the states that are included in this transition. Here you can see the excitation energy that I was just talking about, calculated from the spectroscopic perspective, which is the difference between the electronic states of the neutral species. Another thing that's important is the oscillator strength, which shows that, which describes how intense will be the transition in the absorption spectrum, for example. And here I have summarized it for this species. What you can see here on the right are the natural transition orbitals that can be used for visualizing those unpaired electrons. But that's the same as George was talking in the beginning. It's for your future reference, as you can do it separately from IQ-mol. That's it. Thank you. I believe I was the last one to present the summary.
Great. Thank you so much for that.